All right, good morning, everyone. It's good to be back. Uh, Today, we will learn about sound. I hope you had a good week last week with Cameron, where you started to learn about waves. So you learn about the basic concepts of waves, how to describe it in terms of amplitude, wavelengths, and frequency. So today, we will look at a specific kind of wave, which is sound. Well, last time you learned about the two kinds of waves. Waves can be classified as transverse or longitudinal waves. Sound is an example of a longitudinal wave. And then next week, or even in lecture 3 this week, we will look at light as an example of transverse wave. So just to recap the difference between those two waves, if you disturb the medium this way, a transverse wave will propagate perpendicular to the disturbance of the wave. So the red dot here represents a particle in the disturbed medium. Notice how the particle just oscillates up and down, whereas the wave propagates to the right. The oscillation of the particle is perpendicular to the propagation of the wave. For a longitudinal wave, on the other hand, such as this column of air. Air, of course, consists of air molecules or particles. If there's a plunger on one end and you disturb the medium, again, the red dot here represents the individual particle. For us to easily visualize what happens to the individual particles, notice how the particles just oscillate over a short distance to where they're at. The oscillation of the particle in a longitudinal wave is parallel to the propagation of the wave. So that's the main difference between a transverse wave and the longitudinal wave. It's the direction of oscillation of the disturbed particle to the propagation of the wave. So sound is an example of a longitudinal wave. You can mathematically describe the longitudinal wave in the same way that you describe transverse waves. A here is the amplitude of the wave. K is defined as the wave number given by this equation, and omega is the angular frequency, which is related to the normal frequency. So it's exactly the same form as the transverse wave. So in this lecture, we will focus on sound waves as longitudinal waves. It's exactly how we are able to hear sound. So consider, for example, a speaker on one end. So if you have sound coming out of the speaker will disturb the surrounding air molecules so that the air molecules compress and rarefact. Through the compression and rarefaction of the air molecules, the sound wave is able to propagate. So rarefaction is this low pressure region where you have less air molecules, and compression is, of course, this high pressure region where you have compact air molecules. And through the compression and rarefaction of the air molecules, sound is able to reach our ear. The eardrum in our ear vibrates in a similar fashion, and that's how we are able to hear the sound. So because of the way longitudinal waves propagate, they need a medium in order for them to propagate. And so whenever a wave needs a medium, we say that it's a mechanical wave. And transverse waves, they're quite different because transverse waves can either require a medium like waves on a string, or they can propagate in vacuum like light, which we will learn later on. But for longitudinal waves, they must, the medium is required. Okay, longitudinal waves really need a medium in order to propagate. And so the speeds of the wave, the longitudinal wave, i.e. sound wave, depends on the properties of the medium, right? Because if you think about it, the propagation of the longitudinal wave depends on the compression and rarefaction of the medium through which it propagates, and therefore the speed of propagation of the longitudinal wave depends on two things: the compressibility of the medium and the density of the medium. Okay. And if the sound wave propagates in liquids or in gas, the compressibility is defined by the bulk modulus B, and of course, density rho. So this Greek symbol rho, which we have encountered before, is the density, and therefore the speeds of the sound wave through liquid or gas depends on the bulk modulus and the density. Okay. If it propagates through solid, like solid rod, then the compressibility of the solid is defined by the Young's modulus of the solid material. Young's modulus is defined by the variable y, and it also depends on the density of the solid, which is again rho. Okay. So these equations give you the speed of propagation depending on the properties of the medium through which the longitudinal wave propagates through. Okay. Right? But regardless of which medium the longitudinal wave propagates through, just remember that sound or longitudinal wave is still a wave. So the speed of the wave, of that wave, is still related to its wavelength and its frequency. So you can still use this equation: speed is equal to wavelength times frequency, which is the general definition for a speed, for the speed of any wave, regardless of it, either it's transverse or longitudinal wave. The speed of the wave is equal to its wavelength times its frequency. But if you want to relate the speed of the longitudinal wave to the properties of the medium it propagates through, then you have to consider the compressibility through the bulk modulus in liquid and gas, or the Young's modulus in a solid. Right? Does that make sense? Okay. Yeah. So yeah, the speed can be defined by those equations, but also because the elastic properties, the bulk modulus and the Young's modulus, or the compressibility of a material, depends on temperature. It therefore makes sense that the speed of sound in air also, the speed of sound also depends on the temperature of the material, okay? Because temperature affects the compressibility of the material via its bulk modulus or Young's modulus. And usually we will look at propagation of sound in air. So in air, the relationship between the speed of sound in air to the temperature of air is given by this equation here. 331 meters per second is the speed of sound at 0 degrees Celsius, when the temperature of the air is 0 degrees Celsius, and Tc is the air temperature in degrees Celsius. Right, so for any given air temperature, you can use this equation, substituting the temperature of air into this Tc value, and then calculating the speed of sound in that air temperature. But often we will assume that the temperature of air is 20 degrees Celsius, in which case the speed is 343 meters per second. So I would say that in majority of the problems, if the temperature of air is not given, you can assume it to be at 20 degrees Celsius, in which case the speed of sound can be assumed to be 343 meters per second. Right. Okay, we'll park that a little bit, and we'll use this speed more when we talk about Doppler shift and Doppler effect in our lecture tomorrow. But moving on with sound, we can characterize sound in terms of its two aspects, pitch and loudness. Okay? So when we say pitch refers to how high or how low the sound is perceived by the ear, right? So high pitch sound like the sound from a violin, or low pitch sound like the sound from a bass drum. Okay. But so pitch is something we can perceive, but if we relate pitch to the property of the wave, pitch is determined by the frequency of the wave. Right? Frequency is how many wave fronts are passing through a given point. So high pitch sound corresponds to a high frequency sound. So if you look at these two waves here, high frequency means you have a lot of crests and troughs passing through a given point. This is a high frequency wave that will give you a high pitch sound. Low frequency wave gives you low pitch. So low frequency, you have less number of crests, wave crests or wave troughs that are passing a given point, right? And low frequency sound gives you a low pitch. We will talk more about pitch in the next lecture, but just for an additional information, the pitch that the human ear can perceive ranges from 20 hertz to 20 kilohertz. So that's the frequency of sound we can perceive, which decreases, I mean, the older we get. So the older we get, the lower the more sensitive we are to low frequency sound. Right, so pitch is related to frequency. Now loudness, right, how loud or soft sound is related to the intensity of the sound wave. Okay, right, so we will talk first about loudness. In this lecture, we'll focus more on loudness. And then towards the end, we will talk about pitch, and that will move nicely into tomorrow's lecture, which will again talk about pitch. So loudness is related to intensity. Therefore, let's define what intensity is. Okay, intensity is defined as the energy per unit time across a unit area. Mathematically, you therefore have intensity is equal to energy per time, or energy divided by time per unit area. Okay. Right. Energy divided by time, we learned that that's equal to power, right? Power is how much energy you use up over time. Hence, energy over time is equal to power. In other words, intensity is equal to power divided by area, and therefore the unit will be watts, coming from the unit of power, and area, of course, has a unit of square meters or meter squared. So the unit for intensity is watts per meter squared. Okay, it's useful to understand. I mean, it's useful to remember the unit for intensity being watts per meter squared, because later on I will introduce another measure of loudness, which is decibels, intensity level. And knowing the unit for intensity can help you distinguish between intensity and intensity level. Okay? So intensity is measured as watts per meter squared, coming from the definition power over area. Right, the question now is, what is this area, right? How do we calculate, or how do we determine this area? We can understand what this area is by visualizing or imagining how sound propagates through space, right? So for example, or sound or wave in general propagates through space. So imagine, it's easier to visualize water waves. So imagine a calm lake. Okay? And if you drop a rock or a stone on the calm lake, right, we know that it will create ripples, right? Okay? And the ripples will propagate from the point where the rock was dropped. Okay, so this picture shows you the ripples here. So the ripples propagate from the center where the rock was dropped, and you will see that it sort of propagates in as concentric circles, right? Concentric circles meaning circles centered around that point where the wave came from, the wave originated from. Now, if you translate that to sound waves and imagine that you have here a point source like a speaker where sound is coming from, the sound sort of propagates as circles around the source of sound. Okay? But it's three-dimensional. So you can think of it as a sphere, right? Sound propagating as spheres coming from the point source, the source of sound. Okay, the power is then distributed equally. Power meaning energy is then distributed equally through the area of the sphere. Right. Does that make sense? So therefore, we define the area as the surface area of the sphere, because the sound sort of from the source, the point source, the sound sort of propagates as spheres centered on the source of sound. So the intensity or the loudness of sound depends on the surface area of the sphere, 4 pi r squared, and also the power, the energy of the sound at the source. Okay, right? So power, it's the power at the source, how much sound is coming, power of the sound coming from the source. Okay? It's constant because it's always the same regardless of the distance from the source. So power is the same, right, regardless of where you are in the room, right? Regardless of where you are in the room, the power of the sound coming from this microphone is the same, but the loudness will change depending on the distance r from the source, right? All right, the other thing to notice is that the intensity is inversely proportional to the distance squared. Okay. So that means that intensity follows an inverse square law, which means that the intensity decreases in proportion to the square of the distance from the source. The intensity or the loudness, and that's why the farther you are from the source of sound, the softer the sound you hear, because of this inverse distance square relationship. Okay, the power is the same, right? Let's just say the volume of my voice is the same. The power that comes from the sound coming from my mouth is the same, but because you are at different distances from the source, R is different. The intensity or the loudness of the sound you hear is different because of the distance rather than the power. Good. Right, so let's look at this example to see, to relate intensity, power, and the distance. Say a point source emits sound waves. The intensity 4 meters away is 0.448 watts per meter squared. Then notice the unit for intensity, watts per meter squared. What is the power emitted by the source? Right? It's a rather straightforward application of the definition. Intensity is defined as power divided by area. What we want to find is power, hence power equals intensity times area. The intensity is given. It's the watts per meter squared. Okay. And the area is the area of a sphere, surface area of a sphere, because sound propagates as a sphere originating from the source. Yeah, so intensity that's given times 4 times pi times the distance. So R is the distance from the source. And don't forget there's a square. Don't forget to square the distance. All right, so the power is 90 watts. Right, so what if you moved 8 meters away from the source? So 8 meters, that's double the original distance. What will be the intensity or how loud the sound will be if the distance is double? Okay? If you move 8 meters away from the source. So again, intensity can be found from the power divided by the area. Okay, the question here is what power to use. Right? And it's important to remember that the power is the same regardless of the distance from the source, because it's the power of the origin, where the sound originally comes from. Right, so you can use the power you got from before. Okay, what changes is the distance R. Distance is doubled to 8 meters. Again, don't forget to square the distance. And that will give you an intensity of 0.112 watts per meter squared. Okay. What you'll notice is that if you compare this intensity 8 meters away and the intensity 4 meters away, you will see that if the distance is doubled, the intensity is reduced by a factor of 4. And that's the essence of the inverse square rule, right? Because your distance, the intensity is inversely proportional to distance squared. If the distance is doubled, then the intensity should reduce by a factor of 4. Right. Good. Right, so intensity refers to how loud the sound is. And for the human ear, we can detect a very wide range of intensities from 1 times 10 to the minus 12. That's a very small intensity to 1 watts per meter squared. Right, so yeah, so this 1 times 10 to the minus 12, that's the threshold of hearing. A whisper has an intensity of 1 times 10 to the minus 10, so we can hear that. Yeah, a loud rock concert is 1 watts per meter squared. Of course, we can hear, and that's almost painful right? That's the threshold of pain is 1 watts per meter squared, because the eardrum vibrates so vigorously that we feel the pain. And so we can hear a very wide range of intensities. And because of this wide range, the loudness that we perceive is not actually directly proportional to the intensity, but rather the human ear responds in a logarithmic way. Okay? So instead of looking at loudness in terms of intensity, it's more useful to look at loudness in terms of intensity level. All right, so notice how I add, when one word is added, it totally changes the meaning, right? So we were talking about intensity earlier, measured in watts per meter squared, but it's easier to deal with sound in terms of intensity level. Okay? Intensity level, this is referred to as beta, and it's measured in units of decibels. This is intensity level is the logarithmic counterpart of intensity. So let's look at this intensity level beta measured in decibels. Right, of course, they're convertible. You can convert intensities to intensity levels. So given intensities in watts per meter squared, you can convert that to decibels, intensity level, decibels via the logarithmic function given here. Okay. So that's 10 log of I. I is intensity, beta is intensity level, right? Right. 1 times 10 to the minus 12 in this equation is the threshold of hearing, so it's a constant number that we will assume. And of course, you can rearrange this mathematically to isolate intensity. Say, given the intensity level in decibels, you can determine what's the intensity in watts per meter squared. Rearranging this equation, I've done the rearrangement here, but you can derive it if you want. The intensity will be the threshold of hearing times base 10 exponent beta over 10. All right, so these two equations can be used to convert between intensity watts per meter squared and intensity level decibels. Okay. Now let's look at an example to see how these two are related, intensity and intensity level. So here, a point source of sound has a power of 4 milliwatts, right? Milli times 10 to the minus 3 watts. Okay, we want to find the intensity 2 meters away. So we're given power, okay, and we are given the distance r. Okay, so previously we learned that intensity is related to power over area. In this case, therefore, we are able to calculate the intensity because we're given the power, 4 milliwatts. Don't forget the times 10 to the minus 3, converting milli to watts. And then the area, 4 pi r squared. R is how far away you are from the source of sound. That's 2 meters. Then don't forget there's a square there. All right. So you are able to calculate the power, the intensity, 8 times 10 to the minus 5 watts per meter squared. Okay. What is the sound level in decibels? Okay. At that distance, 2 meters away. So you know the intensity. Converting that, it's essentially a conversion problem, right? Converting intensity watts per meter squared to intensity level decibels, right? So in decibels, you have 10 log intensity, which is what you found earlier. 8 times 10 to the minus 5 divided by 1 times 10 to the minus 12. Okay, so do the division, take the log base 10 times 10 gives you an intensity level of 79 decibels. Right? Okay, I hope relatively straightforward calculations. It's just a matter of distinguishing different terms, right? Power, intensity, and intensity level that then allows you to use the correct equation. Okay, so this example starts with decibels, intensity level. A mosquito buzzes at 40 decibels. Okay, this is intensity level. Calculate watts per meter squared intensity. Okay, so again, intensity and intensity level, it's really just a matter of conversion between watts per meter squared and decibels. Okay, given the decibels beta, the intensity is the threshold of hearing times base 10 exponent beta over 10. Okay, so this is base 10 and this is the exponent, right? All right, so beta intensity level is given. That's 40 divided by 10. Right, that's 4. Use that as the exponent of base 10. Then multiply that with 1 times 10 to the minus 12. You should get 1 times 10 to the minus 8 watts per meter squared as the intensity. Right? Okay. Now, what if a second mosquito sits by the first one and the second mosquito is buzzing at the same sound level of 40 decibels? Okay. What will be the new intensity level in decibels? Right, and this example is sort of related to one of the questions in the assignment where there's a jet plane with 2 engines and 1 engine, 2 engines, of course, giving off sound at some level, intensity level, and 1 engine is turned off. Okay, what will be the intensity of the other engine left? Okay, right, so right, so it's very tempting to say that the new intensity level will be 80 decibels because one mosquito buzzes at 40 decibels and the second mosquito buzzes at 40 decibels. Therefore, the new intensity level will just be the sum of the individual intensity levels and therefore 80 decibels. But this is actually a wrong solution. Okay, you cannot add intensity levels because intensity levels are logarithmic, right? And if you're dealing with logarithms, you don't just simply add logarithms. And therefore, what we can add are intensities. You can add watts per meter squared intensities, but you cannot add decibels, intensity levels, right? So in the same way, you can subtract intensities, watts per meter squared, but you cannot subtract intensity levels, decibels, right? Okay, so the correct way of solving this, right, will be first to find what is the intensity in watts per meter squared. I1 and I2 in watts per meter squared. Okay, you need to find the intensities of the mosquito's buzz in watts per meter squared, and then you add the intensities to find the new intensity, and then convert that to decibels. Okay. And in the previous question, we worked out that 40 decibels is 1 times 10 to the minus 8 watts per meter squared, right? So therefore, if two mosquitoes that are buzzing at the same 40 decibels, the intensity of those two mosquitoes buzzes should therefore be 2 times the intensity for one mosquito. Right, so first find the intensity in watts per meter squared. Okay, and then convert that to intensity level decibels. Okay. So once you know the intensity, it's converting watts per meter squared intensity to decibels. You'll find that the new intensity level in decibels is 43 decibels and not 80 decibels. Okay. Right? Good. Right? And as I said, the same concept holds when you are subtracting intensities, right? You can subtract intensities watts per meter squared, but you cannot subtract intensity levels. You cannot subtract decibels, right? Good. Right, so the key ideas behind intensity is the definition behind loudness, right? Right. We talked about loudness. The key ideas behind loudness is intensity, watts per meter squared, which is related to the power of the sound at its source, and converting intensity to intensity level in decibels. Now for pitch, before we move on to pitch, are there any questions about loudness or intensity or decibels? Right, good. All right, so for pitch, so let's move on to pitch. As I mentioned earlier, to find the pitch, whether the sound as a high pitch or a low pitch, you need to determine the frequency of the sound wave. Right? And last week you already saw this standing wave on a string. So say to determine the pitch of a guitar, the sound of course propagates through the strings of the guitar. The ends of the string on the guitar are both fixed, okay? And because the ends are fixed, the ends are normally a node. So N stands here for nodes, and you derive the relationship of the wavelength, say, of the harmonics of the standing wave on a string, right? This is the first harmonic of the standing wave of the string. If you relate it to the length of the string, right? That's the length of the string. Notice that in the length of the string, you can fit half a wavelength. Therefore, the first harmonic is the first harmonic is related to the length of the string being equal to half the wavelength of the string. And from there, you can find the frequency from the definition of speed. This equation came from V is equal to lambda F. After determining the wavelength of the wave in relation to the length of the string, you can find the frequency of the harmonic on the string, and that then derives this equation. So for each harmonic, that corresponds to a certain frequency or a certain pitch that the guitar can produce in terms of sound. Now, for wind instruments, such as flutes, trumpets, they create standing waves in air columns. Okay, so for wind instruments, sound is produced, in air columns, as I mentioned. But unlike string instruments like the guitar, in string instruments, both ends are fixed. For wind instruments, you have either a free end, both free ends, or one of the ends that are free. Okay, so for wind instruments, say for an open end, okay, this is the ends of a wind instrument. Because the ends are open, there's nothing fixing the sound wave at the ends. Therefore, the ends are naturally antinodes. Okay. So A here stands for antinodes. That's the A there, antinode. Okay, and in the middle, you have a node. Right. So this figure here on the left just shows you the positions of the antinodes and the nodes in relation to the drawing of the sound wave on the right here, right? So this is for an air column with both ends that are open. And as I mentioned earlier, if both ends are open, then both ends should be antinodes, because there's nothing fixing the wave at both ends, right? So you have antinodes here. Notice for the first harmonic, if this is the length of the wind column, okay, the length of the wind column can fit half a wavelength. If you draw a wave, sort of try to draw a wave like this, and the wave sort of repeats itself like this. So, right, one wavelength is from here to here. One wavelength is defined as the distance through which your wave will repeat the pattern, right? So from this point to that point, that's one wavelength. Therefore, half of that will be half a wavelength, and that half of that is fitted through the length of the air column, and therefore the wavelength will be twice the length, or the length can accommodate half the wavelength, and therefore the first harmonic in your open end air column will have a frequency of V over lambda, or V over 2L. In terms of pitch, because we said that pitch is related to the frequency, the pitch that this air column can produce will therefore depend on the length of the air column L and how fast the sound propagates through the air column. Okay. Now for the second harmonic, you simply add a node. Okay. You simply add a node at each step, keeping both ends as antinodes. So if you keep both ends as antinodes because it's always open, both ends are always open, you necessarily add a node at each step, okay, and the frequency changes according to this equation. Okay. Third harmonic, so notice how in first harmonic you have one node, in second harmonic you have two nodes, in third harmonics you have three nodes, and so on. And these equations give you the relationship between the length and the wavelength of the harmonic, as well as the frequency of the harmonic. Okay. For an air column with a closed end, okay, so you have here one end that's open and one end that's closed. Okay. Again, at the open end, because there's nothing holding or fixing the wave, the open end should be an antinode, right? And the closed end should be a node. Again, the figure on the left is an illustration showing where the antinodes and nodes are, and the figure on the right gives the drawing of the wave. Right? So these two correspond to each other. On the left, you have an antinode because it's an open end. On the right, you have a node because that's a closed end. Okay. Right. If you relate the length, so if this is the length of the air column, and you relate the length to how much of a wave is contained throughout that length, you'll see that this is 1/4 of a wave. So in that length, 1/4 of a wave is contained, and therefore the wavelength of the sound wave in that air column is equal to 4 times the length of that air column. You can then derive the frequency that will give you the pitch using the relationship V is equal to lambda times frequency. Hence, you can relate the frequency to the length of the air column. Okay, so that gives you the first harmonic that is produced by the air column with a closed end. For successive harmonics, you add a node and an antinode at each step, because this open end needs to always be an antinode, and this closed end needs to be always a node. Hence, you have to add a node and an antinode to maintain this node at the closed end and this antinode at the open end. And therefore, for an air column with one closed end, you'll only have odd harmonics: first, third, fifth, seventh, and so on. Notice how there's no second and there's no fourth harmonic. There are no even harmonics. Okay. But these equations give you relationships of how to calculate the frequencies of the harmonics in relation to the length of the wind column. Right. So this slide summarizes the 3 types of instruments. If you have a string, both ends are fixed. There are always nodes at both ends. And these equations you can use to find the wavelength and the frequencies of the string. If you have a pipe, an open pipe, both ends open, both ends are always antinodes, and these equations relate the wavelength and frequencies to the length of this open pipe. For a closed pipe, one end is open, the other end is closed. The closed ends will always have a node, the open end will always have an antinode, and you can use these equations to calculate for the wavelengths and the frequencies of the wave produced by this closed pipe. And just to make it complete, here are some examples of musical instruments for each kind of open, closed pipe, and strings. All right, and the sound, the pitch of the sound that each of these musical instruments produce is of course related to the frequency of the sound that is produced by the harmonics, which you can calculate using these equations here. Good. All right, so that summarizes our lecture for today. We talked more about loudness related to intensity, and then we started to talk about pitch related to frequency. In our lecture tomorrow, we will continue our discussion with pitch or frequency, talking about Doppler shift and beats. So are there any questions? If there are no questions, then I'll let you go and I'll see you tomorrow in the lecture. If you have any questions, of course, feel free to, you can ask me anytime. All right, so have a good day, everyone, and see you tomorrow.